of salt and the pH of their solutions. Salt formed by the reaction between acid and bases in definite proportions undergo ionization in water. For example, the reaction HCl plus NOH gives NaCl plus H2O. NaCl on hydrolysis gives Na plus Cl minus. The process of interaction between water and cations or anions or both of salt is called hydrolysis. Salt of strong acid and strong bases simply get hydrated and do not hydrolyze. For example, NaCl on hydration gives Na plus Cl minus. Thus, solution of salt of strong acids and strong base are neutral. Now we consider the hydrolysis of the salt of the following types. The first one is the salt of weak acid and strong base. For example, the mixture of CH3COH, which is weak acid, and NaOH, which is strong base. Sodium acetate ionizes in aqueous solution. CH3CONa reversible, CH3CO- plus Na plus. Acetate ion thus formed undergoes hydrolysis in water to give acetic acid and OH minus. That is CH3CO- plus H2O reversible CH3COH plus OH minus. Acetic acid being a weak acid remains unionized in solution, thus increasing OH minus ion concentration in solution, making it alkaline. This implies that pH is greater than 7. The second one is salt of strong acid and weak base. For example, the mixture of HCl, which is strong acid, and NH4OH, which is weak base. Ammonium chloride, that is NH4Cl, dissociates in water. Ammonium ion, that is NH4 plus, undergoes hydrolysis with water to form NH4 plus H2O reversible NH4OH plus H plus. Ammonium hydroxide, that is NH4OH, is a weak base and thus remains unionized in solution, thus increasing H plus ion concentration in solution, making it acidic. This implies that pH is less than 7. The third one is salt of weak acid and weak base. For example, the mixture of CH3COH, which is a weak acid, and NH4OH, which is also a weak base. Considering hydrolysis of ammonium acetate, we get CH3CO- plus NH4 plus H2O reversible CH3COH plus NH4OH. CH3COH and NH4OH also remains into partially dissociated form, which is given by CH3COOH reversible CH3CO- plus H plus and NH4OH reversible NH4 plus OH minus, and also H2O reversible H plus OH minus. Text. Amines. Amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. For example, methylamine, that is CH3NH2, codeine, quinine, and nicotine. Let us take an example. The ionization constant of HF is 3.2 into 10 to the power minus 4. Calculate the degree of dissociation of HF in its 0.02 molar solution. Calculate the concentration of all the species present, that is H3O plus, F minus, and HF in the solution and its pH. Now moving on to the solution. The following proton transfer reactions are possible. The first one is HF plus H2O reversible H3O plus F minus. Ka of this reaction is equals to 3.2 into 10 to the power minus 4. The second reaction is H2O plus H2O reversible H3O plus OH minus. Kw of this reaction is 1 into 10 to the power minus 14. As Ka is very greater than Kw, then 1 is the principal reaction. So, the principal reaction is HF plus H2O reversible H3O plus F minus. Initial concentration of HF is 0.02 and that of H3O plus and F minus is 0. Let equilibrium concentration of HF is 0.02 minus 0.02 alpha and that of H3O plus and F minus is 0.02 alpha each. Substituting equilibrium concentration in the equilibrium reaction for principal reaction gives Ka equals to 0.02 alpha to the power 2 upon 0.02 minus 0.02 alpha, which on simplifying we get 0.02 alpha square upon 1 minus alpha, which is equals to 3.2 into 10 to the power minus 4. We obtain the following quadratic equation. Alpha square plus 1.6 into 10 to the power minus 2 alpha minus 1.6 into 10 to the power minus 2 equals to 0. The quadratic equation in alpha can be solved and the two values of the roots are alpha is 0.12 and minus 0.12. The negative root is not acceptable and hence alpha is 0.12. This means that the degree of ionization, that is alpha, equals to 0.12. Then equilibrium concentrations of other species, that is HF, F minus and H3O plus are given by concentration of H3O plus equal to concentration of F minus, which is equal to C alpha. On substituting the value of alpha, we get 2.4 into 10 to the power minus 3 molar and concentration of HF equals to C times of 1 minus alpha. On substituting the value of alpha, we get 17.6 into 10 to the power minus 3 molar. Since pH equals to minus log of H plus concentration, which is equals to minus log of 2.4 into 10 to the power minus 3, which on simplifying get pH equals to 2.62. Hence, we get the answer.